So we're up to lesson 3 for Unit 2, our interference unit, and we've actually seen the bulk of the important stuff in the last lesson. In this lesson, we're going to talk about why the interference pattern briefly goes away and then comes back, goes away and then comes back. Now, it's actually not a physics AP topic, so don't tell anybody that we're talking about it, but it's pretty obvious that it's happening, so I think we should go and take a look and see where that pattern comes from. And can we make predictions about how big the openings are based on the pattern? So the issue is this: when light waves go through a narrow opening, it fans out, but there are sections that don't actually get hit on the back wall. Now again, I just put a picture of a guy there at the college board saying, don't talk about that, okay? But we're going to talk about it just so that we can fully understand the story that you see. That's what creates these little patches of darkness where the whole pattern diminishes and then comes back for a while, then diminishes, then comes back for a while. So I'm going to call these the dark patches of nothingness, as opposed to the little tiny spaces in between the dots where it goes bright, dark, bright, dark, bright, dark, bright, dark, bright, dark, and then it goes, oh, dark patch of nothingness, and then comes back, bright, dark, bright, dark, bright, dark. And so today we're going to talk about those dark patches of nothingness, which each get a name, right? On either side of the center, we're going to say, hey, that's the first dark patch, that's the next dark patch. And it's pretty neat to see how the math actually dials that in and figures out where they'll actually be. So this happens because each one of the single slits has an issue with its fanned out diffraction pattern. And it turns out it's all related to how wide the opening is. So I'm going to call the size of the slit measured across, I'm going to call that A for aperture, as opposed to the D, that was how far it was from the middle of one opening to the middle of the next. So the A is actually less than the D. It's smaller than the spacing from one slit to the next, measured center to center, right? Often it might be like 5 times, 6 times smaller, right? It could be a really, really small dimension. It could be 1/100 of a millimeter. And it does create these dark patches of nothingness. Now, I've just grabbed a couple of graphics from the internet just to try to show you what's going on here. So the graphics aren't perfect for what we're doing, but they're pretty close. Okay, and you're going to hear me talk a lot about these dark patches. And so there's this fanned out pattern as it hits the wall, right? I'd have my laser over here, and it's sending a little beam of light into this narrow little slit of width A, maybe 1/100 of a millimeter, and it hits the whole back wall, kind of fans out. When you go all the way across the classroom, maybe many meters to the other wall of the classroom, and it fans out across the wall. It might be pretty dim, right, because the energy is spread out, but it's kind of hitting the whole wall. And then there are these dark patches. And so we're going to name them, and we would name them like this. The first dark patch on either side of center is going to be patch 1. Let's use the letter M instead of N, because we used N for the intense little dots. Let's use M for where the dark patches are. And so there's no dots in the center here, just this big, wide fringe of light, right? And then the next dark patch of nothingness from a single slit would be here. Also on this side. You might hear people talk about the central fringe, the central little bulge of light. Okay, that would be here. And I want to show you where those dark patches of nothingness would be. Okay, and if it's a 2-slit pattern, then you'll actually see dots inside that central fringe, right? Instead of a big wide band of light, it'll be like dot, 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 dot. But if it's a single slit, it'll just be smudge, right? A single slit would look more like this, right? Just smudged out. But there would be a dark spot, and then the smudge would come back. And then the 2 slits, the smudges are dots instead of a smudge. But they all have these patches of nothingness. So let's see if we can see why and where they'll actually be. Down here on the bottom, again, just more quick little graphs I've grabbed from the internet. Things I'm noticing. Yeah, this is a single slit in this graphic that I've grabbed from Google. The light's fanning out, but it does have some spots along the wall there where it doesn't seem to do a good job of fanning out. And so right here, right there, that would be M equals 1. And you can see you've got that confusing graph of brightness, right? Really popular in physics textbooks. just recording how bright the light is on the back wall. And so it's not quite as bright in this next fringe, right? And then, oh, dark patch of nothingness. And I need to tell you that usually by the time you get to about m equals 2, usually it's so faint you can't see it with your human eyes. So we typically won't go much past m equals 2, maybe m equals 3. Probably not as far as what you see in this picture here. Okay, so that's the deal, right? It looks just like that. And now on the next page, I want to show you why it does that and how the math actually works. But remember, this is beyond PhysicsAP, and it's going to get a little bit more technical than what we saw for the double slit pattern. So we've got, over on the right, our wall of the classroom. Here's the screen, or the wall, where the pattern shows up. Got my single slit over here. In comes my laser light. You can see that there's some size to this opening, right? So the aperture size is this big. Could be 1/100th of a millimeter. And now that light's going to go through, and totally not to scale, but on the other side of the classroom, okay, got my center line here. Other side of the classroom, there's going to be this bulge of light like this. And then it's going to get dark. And then the light fans out a bit again, right? You're thinking, oh, it's finished fanning out. No, 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 there's some more fanning out right here. Then it gets dark, and oh, maybe you can see a little bit more. And so you have these patches, right? Like you can see we've got m equals 1, the m equals 2 patch, and then up here as well, right? This is the m equals 1 and the m equals 2 patch. Okay, so what is it that's so special about those places that's causing it to actually go dark there? Well, the best way that I can describe it is we have to zoom in a little bit more than we did in the last picture, in the last lesson. We have to zoom in a lot on this slit. And imagine that this slit is wide enough that if we were to play that game, you know, with the little Huygens radiators, the little Huygens singers, we could actually sneak a few in. And I'm going to draw in some with different colors and shapes just so you can kind of get a feeling for what happens. I'm going to put a little blue dot Huygens radiator right there, and then just past center, another blue dot. Eventually I'm going to draw 6 of these. And now maybe, I don't know, maybe a green triangle. And a green triangle. And now maybe an orange square. And an orange square. I just want to be able to quickly identify them just kind of based on shape and color. So there are 6 little Huygens singers, little Huygens radiators that have made their way up to that opening, up to that door, and they're now going to start singing. And depending on where you are in the wall, they may start interfering with each other. So this is neat. These are waves from a single opening that are going to interfere because some spots on that opening are a little farther from you, the observer over here at the wall, than other places, right? So here you are kind of looking over here at m equals 1. And it's a little bit different path length from one blue dot to the other blue dot to you. So let's draw those in, right? So here you are wondering, why is it dark here at that spot? Well, let's look at the blue dots. Remember, this is not to scale, so those lines are basically parallel. They're so close to being parallel, they might as well be. And it looks like this is angle number 1. Angle to the first feature. The first interesting thing to talk about. Okay, well, that blue dot, which is halfway down, it's a little bit longer from there to you than the top one, and it's all about that space right in there. That tiny, tiny extra little bit of path length is going to cause this problem. Because if that tiny length is off by half a wavelength, then it will interfere with the other blue dot. And by the time the waves from the 2 blue dots get to you, they will cancel. So blue dot cancels with blue dot if this is off by half a wave. Now, if you keep expanding that picture, by the time you get all the way down to the bottom, from that blue dot to that orange square will be off by a full wave. But from blue dot to blue dot, it's off by half a wave. So the 2 blues cancel. The 2 green triangles cancel each other out. The 2 orange squares cancel each other out because their pairs are always off by half a wavelength compared to the other one. Let's zoom in like we did last time just to get a little bit better feeling for how this is looking. Right? So we've got blue dot, and then all the way down here at the bottom. And I'm going to draw my right angle triangle like this. Here's the opening. There's A, right from there to there. And then the triangle went like that and like that. And our theta went here. So that extra little blue path would be in here. That's out by half a wavelength. By the time you go all the way down to the bottom and look at the math, that would be out by a full wavelength. That's the tricky part, is respecting that, right? So this is a half wave, little canceling. And by the time you do that similar triangle, this would be a full wavelength that you're out. But the partners, the two blue dots, are out by half a wavelength. And the two green triangles, their paths are out by half a wavelength. But from one edge to the other edge, you're out by a full wavelength. That's for m equals 1. You have one pairing, right, of canceling that's there. For m equals 2, you actually have two sets of pairs on your way through that shape. So you'd actually have to have not 2 blue dots, but 4 blue dots in order to get the whole thing kind of dialed in to figure out how all the cancelings are going to happen. In any case, here's the equation that talks about where those dark patches are. And I have good news and bad news. The good news is it's the exact same equation in terms of style and feel as the one for the two-slit interference. This time, though, it has an A instead of a D, right? And then sine of an angle. And you're like, well, which angle? And I'd say, yeah, exactly. Which angle? Which one do you want to talk about? Which feature, which M number do you want to look at? Right? You can talk about the first dark patch or the second dark patch, whatever you want. That's going to end up equaling your dark patch number, that integer, multiplied by your wavelength. Usually, we use this to try to find dark patches. So if that's your plan, if you're like, yeah, I'd like to find dark patch 1 or dark patch 2. Okay, so to find dark patches, you would be putting in m is equal to 1 or 2 or 3. Usually after 3, we kind of get bored of the game, but they would go in here. If you desire to find this place here where it actually gets a little bit bright again, you know, in between dark patch 1 and dark patch 2, we can actually locate that mathematically as being like 1.5. So if you desire to find the little bright fringes in between the dark patches, you can do that. What you would do is you'd be putting in an m value of, the first one that makes sense actually is here. You'd put in 1.5 or maybe 2.5, and those numbers would go in here. So the equation's designed to find dark patches, which is the exact opposite of the one for interference, where it was designed to find bright dots, right? So when you put D's in, it's bright dots. When you put A's in, you actually get these dark patches of nothingness. And we still have the exact same little approximation that we had before. I've got a lot of extra room here. We have that approximation where tan theta and sine theta are basically the same thing, but now that turns into, it would be, I'm just going to make it look, I want to make it look like the notes we had last time. So let me just go back and take a look here. How did we write that? We went x over L. Yeah, okay. Actually, we'll write this a couple of ways here. So you could say that x, the distance to that dark patch, divided by L is equal to m lambda all over A. If you're planning to use this approximation to find the x's, well, you can solve for x if you wish. That would be m lambda L all over A. That works great as long as the angles are less than about 10 degrees, because that approximation assumes that sine theta and tan theta are the same size. Now, in situations that are like, let's go back to this little picture here. In situations that look like this, where the size of the opening A, let's get rid of this, where the size of the opening A is actually small, really, really small compared to D, you'll notice that you get a whole bunch of dots before you finally get a dark patch of nothingness. In fact, if you had a D, a distance from slit to slit, that was 10 times as big as the A, you'd actually get like 10 dots down before you got to the dark patch of nothingness. So often for AP exams, because they don't want to talk about these dark patches of nothingness, they'll actually say, and this is correct, right? They do have their physics right. They'll say, well, let's imagine that the D is much, much bigger than the A. And so if that's the case, you just see a whole bunch of dots before you run into that first dark patch of nothingness. And that's their way of avoiding the dark patches of nothingness. But if you want to know where they are, this equation will get you there. It looks just like the equation we had for interference dots, but now you're going to find the dark patches of nothingness. And it's neat the way it's paired up with things that are halfway along the slit, right? And it's out by half a wavelength. And then you get those pairings where things cancel out. And so that finishes up our third day.